This is Nevika Academy. Today we want to look at closure. Kindly subscribe if you have not yet subscribed to this channel. Share also with your friends so that every time I post anything here, they are the first one to get notification. Okay, welcome. Closure. Closure is one of the topics in relay analysis, and this is the definition of closure. So we let A be a subset of X. Then the closure of A, which is denoted by A bar, is given by the union of A, set A, and its derived set. Where A is an derived set, A prime is an derived set of A. Remember, the derived set is a set of limit points. So if A is closed, then you'll find A is equal to A bar, or is equal to the closure. A closed set contains all limits. Since a closed set contains all its limit points, and that will imply this. So that's basically what we mean by closure. That the derived set will be contained in A. All its limit points of both the closure set and the set A are equal. So if that happens, this becomes true. Let's define another set called the set. So a subset of A of X is said to be this if it happens that its closure is equal to the set. The closure set is equal to the set X. That is, every limit in X is a limit in A. So if you happen that the limit in X is also a limit of A, then you find that that one is a Day's set. Example: set of rational numbers is Day's to real numbers, because you'll find that every limit in rational number set is also a limit in real numbers. Okay, compactness. And by this we first define compact set. So we let D, which is defined in this form, and S be an empty set, some set of real set. We say D is open cover. Of C if S is a subset. We say D is an open cover of X, if S is a subset of D. So if you find that S is a subset of D, we'll say that D is an open cover of X. So S you find is contained in the union of all the D's. If in addition the finite number of the indices, say 1, 2, that way to n, can be found in such that S is contained in the union of those D's, then we will say that S is a compact. Is said to be compact in the real set. If all the S's are inside that union, then you say it's a compact set. That's the key thing. All S's are in the union. So we simply say that a subset S of real set is compact if every open cover of X contains a finite subcover. Okay, so it's we say that a subset S of a real set is compact if every open cover of X contains a finite subcover. We'll say that S is compact. Example: every finite subset of K, which is a subset of real set, is compact. Let's prove this. Let us have a K which is finite, so we define it like that way. So it's a finite set of a real set, and we have an D, which is now our cover. Be an open cover for K, for each i's ranging from 1 to n. Then D, from D that contains xi's. So there is a set Di from a D that contains xi, since D is an open cover. So it will follow that there's a D which is a cover, open cover, then it will follow that this is true. Then it follows that the family of Di's that way also covers K. That's what we are calling subcover. And if there is a subcover of this, if there is a cover, then there is a subcover of this, then we'll say that every finite set is compact. Compactness comes in because we have seen that a subset S of a real set is compact if every open cover of X contains a finite subcover. So it's just enough to show that there is a cover and there exists another subcover for that D. And if that happens, then we are all done that every finite subset of K is compact. So compactness will be proven. Let's show, number 2, let's show that this one is not compact. We simply want to show that there is a cover, and then we see whether this cover have a subcover. Remember, this comes in when there is closure. So let's A and B divide that. That is our open level for each n of the natural set. Then if we have H, which is this H here, which is contained in this, the union of this, that, so that An is defined in that is an open cover. It will be open cover. That's clear, you can see that. However, this set here is an infinite subcover. It's an infinite subcover. It's an infinite subcover. Infinite subcollection of A. Okay, and if we let M to be the maximum of these, and then their union follows as that, we'll see that this is -1 to M, because this is basically equal to AM. It's basically equal to AM. Okay, which implies that clearly that the union fails to contain H, because we know our H is basically this. So you can see that our H is not inside this, and N's H is not compact, and N's H is not compact. Another example is that the null set is also a compact set. That's obvious because you have a subcover, a cover which is empty, and this subcover also still being an empty set. And then the set S to this, we know this is bounded, but we're saying it's not closed. It's not closed. A reason being its limits. One of the limit, which is particularly 0, is outside there. It's not inside the set. Then the set, this set is not compact set. We know it is bounded, but it's not closed. It's bounded, but it's not closed, because it has 0 also, which is not inside the set. If you have a question of any of the examples here and need more elaboration, can you leave a comment? I will be grateful to check it out. Make sure you subscribe if you have not yet subscribed so far. Share also with your friends so that they get to understand these basics of data analysis. Okay, kindly subscribe and share with your friends. Until next time.